All right, good afternoon, good morning, everyone. This is Galen Barbos from Lawrence Berkeley National Laboratory. Welcome to today's webinar, where we'll be sharing some highlights from the most recent edition of our annual Tracking the Sun report. I'm joined here by a couple of my colleagues, Naeem Darguth and Eric O'Shaughnessy. I think Sydney Forrester is probably also out there as well. Before we get started, though, I want to just kind of run through a few basic housekeeping items. So first, the slide deck will be available. In fact, it is essentially already available. The report is basically the slide deck that I'll be presenting here, and that report is posted online at trackingthesun.lbl.gov, the URL at the bottom of the slide here. So if you want the slides from the webinar, you can just go there and download the report itself. We are also going to be recording the webinar, and we'll post a recording online as well at that same address if you want to go back and listen to it later or share it with colleagues. We're going to have some time at the end for Q&A. And so I just ask all of you to enter any questions you might have into the Q&A box that you hopefully see on the bottom of your screen. I would just ask that there's also a chat box. Try not to use the chat box. Rather, enter your questions into the Q&A box, and Naeem will be queuing those up for the Q&A session at the end. So feel free to enter those questions as we go. So with that, let's begin. So many of you, I suspect, are roughly familiar with this report. For those that are not, Tracking the Sun focuses on summarizing trends related to the installed price and other characteristics of grid-connected distributed PV systems in the US. And I'll say a little bit more in a few slides about how we define distributed. This edition of the report focuses on projects installed through 2020 and describing trends related to various project characteristics, system size, equipment type, etc., as well as installed price trends, both based on median prices over time and comparing across different states, as well as variability in pricing. We spend a fair amount of effort and real estate in the report looking at the dispersion in prices across projects and kind of trying to identify some of the drivers that impact price diversity across projects. In addition to the report, which, as I mentioned, is essentially this PowerPoint deck, we've also published a number of accompanying products listed on the right-hand side here. So we have, for the first time, a short kind of executive summary style narrative brief, which essentially takes the place of the long narrative technical report that we've previously done. So that's available for folks who are interested in kind of a short, 5-6 page summary of the report. We also have a data visualization tool where you can go and kind of play around with the data online and kind of cut the data in different ways. We've also posted a public version of the underlying project level data set that we use for the analysis in this report. And then finally, we've published an Excel file that contains basically the summary data tables underlying each of the individual figures, as well as the figures themselves, if you care to look at those. And all of those items are available at the website shown here. So with that, let me just say first a few words about the data that we use for the report and what we do with it. So the Tracking the Sun data set is based on project level data, so individual distributed PV projects. That data we obtain each year from a variety of different state agencies and utilities and other organizations around the country. This year, we had a total of 63 entities across 30 different states that contributed data to the report. A few key definitions So throughout most of the report, we'll segment the data into the 3 different customer groups shown here: residential, small non-residential, and large non-residential. The distinction between small and large non-residential is based on a size threshold of 100 kilowatts. In the large non-residential segment, there's an upper size limit of 5 megawatts for ground-mounted systems. Anything larger than 5 megawatts that's ground mounted, we call utility scale, and those systems are covered in a separate Berkeley Lab report that should be coming out soon. But any ground mounted systems less than that size are included here, as well as roof mounted systems with no upper limit. So even roof mounted systems above 5 megawatts get included here. This slide here just summarizes a few aspects of the data cleaning process. I won't go through all of this. I will just note that there are essentially 2 different data sets that we use for different portions of the analysis. We have our full sample, which is just the entirety of the data set. And that's what we use for the figures that describe kind of basically anything other than installed prices. For the installed price related analysis, we use kind of a subset of that larger sample where we remove systems, obviously, that are missing installed price data, as well as removing any third-party owned systems, any systems that are co-installed with battery storage, and any self-installed systems. And we remove systems in those latter 3 categories really just to try to maintain some semblance of comparability when we look at kind of price trends and differences across regions. Here we see the sample size compared to the overall US market. So in total, we had about 2.2 million systems in the data set this year, installed through the end of 2020. That represents a little under 80% of the total US distributed PV market. The installed price sample is about half of that. So we're basically kind of dropping half of the systems in the sample when we look at installed prices. Here we break the sample out by state. Again, comparing to the US market as a whole. I'll just note a few quick things here. First, you can see that California, which is the dark blue segment, dominates our sample as it does the US market as a whole. But whereas our coverage of California is virtually complete, our coverage in some of the other states is not. And so for that reason, our sample skews more heavily towards California than the market, the overall US market, at least on a proportional basis. Most of the larger state PV markets are pretty well represented in the sample, with a few exceptions. Where our sample, I think, tends to have the kind of the poorest coverage is in some of those smaller state markets. So just something to keep in mind as we kind of walk through the trends. So with that, let's look at some trends related to project characteristics. So here we look at trends in system size over time, residential on the top, non-residential on the bottom. And as you can see, system sizes have been getting larger over time. For residential, they've grown from about 2.4 kilowatts back in 2000 to 6.5 kilowatts last year in terms of median system sizes. And that trend is being driven partly by declining costs. So as PV has gotten cheaper, customers can afford to install larger systems. It's also being driven in part by increasing module efficiencies. So as modules have gotten more efficient, you can pack more kilowatts on a given roof space. And so that has also, of course, contributed to this upward trend. On the non-residential side, median prices have grown over time. What's maybe a little bit more stark is the rise in system sizes at the upper end of this distribution. And that just reflects the kind of growing prevalence of relatively large systems. The other thing to note in that non-residential figure on the bottom is that the distribution has a very non-normal shape to it. The median non-residential system size is relatively small, just 42 kilowatts. So most non-residential systems are in that kind of smaller group, but obviously, there's a growing portion that are above 100 kilowatts, which is again our threshold for large non-residential systems. Here we compare system sizes by state. I would just note, looking at the residential figure on the top, that system sizes in California are relatively small, and so that tends to naturally pull the median for the U.S. down. 6.5 or 6.4 kilowatts was the U.S. median system size shown on the last slide. Most states, though, have median system sizes of at least 7.5 kilowatts or more. For the non-residential figure on the bottom, the scaling makes it difficult to compare median sizes, but what's perhaps more interesting is kind of looking at the range in system sizes across states, where you can see kind of a handful of states led by North Carolina where large non-residential systems are much more prevalent. Here we see trends in module efficiency over time. On the top figure, you can see that median module efficiencies in all three customer groups have risen steadily over time, and to a significant degree that reflects the growing market share of monocrystalline modules, which you can also see in the bars in those figures. Module efficiencies do vary quite a bit. You can see that in the distributions on the bottom. So, among residential systems, for example, last year, module efficiencies might have ranged anywhere from 16 to 22% across systems in the sample, with those on the lower end of that spectrum primarily consisting of systems with polycrystalline modules. And then at the very upper end, you have some systems that are kind of premium efficiency modules, above, say, 21% efficiency. Here we show trends in storage attachment rate. So storage attachment rate refers to the percentage of PV systems installed each year that include storage. And you can see in the figure on the top that residential attachment rates have been growing steadily. About 8% of the systems in the sample last year included storage. That number, 8%, certainly overstates the actual US average residential attachment rate. In a separate study, we estimated that to be about 6% last year, and that just has to do with kind of the composition of our data sample. On the non-residential side, attachment rates tend to be lower, and in the large non-residential segment, you can see some big fluctuations there that largely reflect some happenings in the California market. Comparing across states, on the bottom, the kind of standout here is Hawaii, which really is in a class of its own in terms of storage attachment rates, where roughly 80% of all residential systems and 40% of small non-residential systems in Hawaii last year included storage. California is lower than that, about 8% for residential. And then outside of California and Hawaii, you can see a few other states that have relatively high levels of activity. Washington State, for example, where our data primarily come from a single utility. And then in the large non-res segment, you can see that in Massachusetts, about 20% of the systems last year included storage. Here we show trends related to inverters. The figure on the top shows the market share of systems with module level power electronics, so either microinverters or DC optimizers. And you can see that in the residential segment, basically those technologies have kind of taken over the market. Essentially 100% or roughly 100% of residential systems last year included one or the other of those. The numbers are a little bit lower for small non-residential systems, though still a large majority. And then in the large non-residential segment, module level power electronics are considerably less common, though you can see that the share of systems using DC optimizers has been steadily growing and is about a quarter of all systems installed last year. The figure on the bottom shows trends in inverter loading ratios, which is the ratio of the module nameplate capacity to the inverter nameplate capacity. This is, definitely in the technical weeds. I won't say a whole lot other than just to note that these inverter loading ratios have generally been rising over time. Here we see trends related to mounting configuration and panel orientation. So in the figure on the top, you can see that ground mounting is almost non-existent among residential systems, is somewhat more common for small non-residential systems. And then within the large non-residential segment, about half of all of those systems are ground mounted, and about 10% have tracking. The figure on the bottom shows trends in panel orientation. On the left, those trends over time. We see that south-facing systems previously represented, almost the entirety of the sample, but over time, module or panel orientations have diversified a bit. Still, a slight majority of systems are south-facing, but significant portions are also west and east-facing as well, though those trends have kind of stabilized over the last 4 or 5 years. The figure on the lower right just provides a little bit more granularity, looking at 2020 installations and segmenting out the data by customer type. And the main thing to point out there is that south-facing systems are more common within the non-residential segment, no doubt because many of those buildings have flat rooftops, which allow for more optimal orientation. Trends in third-party ownership are shown here. On the residential side, you can see that the TPO market share, or at least the sample share, has been declining over the past few years. This is consistent with what we see in the broader market as well. About a third of the residential systems were third-party owned last year, compared to almost 60%, maybe 6 or 8 years ago or so. On the non-residential side, TPO shares are generally lower, or historically have been lower, and we don't see that same kind of downward trajectory. There certainly is some movement year to year, but not such a clear downward trend as what we see on the residential side. Comparing across states, in the figure on the bottom, you can see quite a bit of variability in TPO shares state by state. In general, those shares tend to be higher in states with relatively rich incentives, either rebates or solar renewable energy certificates that have relatively high prices, as is the case in DC, Massachusetts, and New Jersey. And then finally, here we look at trends in customer segmentation over time for within the non-residential group. So non-residential systems, most of them are installed on for-profit commercial buildings, about 70%. The remaining 30% are split among different types of what we call tax-exempt customers, so either schools, governments, or nonprofit entities. The figure on the bottom provides that breakdown by state. You can see pretty consistent trends across states. We also show there the percentage of both commercial and tax-exempt systems that are third-party owned. And not surprisingly, we see that those TPO shares are much higher for tax-exempt customers because third-party ownership essentially allows those customers to monetize the tax benefits that they otherwise wouldn't be able to do. So with that, let's turn now to looking at trends in installed prices. A few kind of general notes here. I won't run through all of these. I think I'll just emphasize the first one, which is to clarify that when we talk about installed prices here, we're referring to the upfront price that the PV system owner paid prior to any incentives. So the figures here show trends in median prices over time. On the top, over the long term, median prices have fallen by about 40 cents per watt annually on average, but that trajectory certainly has been uneven over time. We've seen periods where prices were falling much more rapidly than that, but since about 2014, the trajectory has tapered off, and we've seen on average about a 10 to 20 cent per watt drop per year across each of the segments. Over the last year, 2019 to 2020, within the residential segment, median prices actually were flat at about $3.80 a watt. In the non-residential segments, they kind of basically continued on that recent trajectory, falling by about 20 cents per watt per year. The recent tapering off that we've seen in median installed prices partly is just a reflection of the underlying trajectory in module prices. And you can see that in the figures on the bottom where we show a module price index. And you can see that module prices, they fell very rapidly for a period of 4 or 5 years, kind of in the middle of the time span shown, and then have tapered off, though are still falling. The soft costs, which are sort of imputed within our analysis here, those are the solid lines in the figures on the bottom. Those soft costs have also been falling over time, on average by about 10 to 20 cents per year. But those soft costs tend to be stickier, and especially when looking at things like customer acquisition costs and some of the financing costs that are now embedded in the installed prices for projects that are loan financed. That is also tending to dampen the price decline over time. And in fact, we can see in the very last year, in the residential side, those residual soft costs actually ticked up a little bit. So those trends showed US medians. Here we look at trends in state level median prices over time. The year-over-year trends, which are shown by the darker bars, those tend to be pretty volatile. So on the residential side, you can see some states saw prices increase year over year last year. Others saw prices decline. Over the long run, though, state level pricing trends tend to converge more or less around the national trend. In most states, you can see, at least looking at 5-year averages, have seen typical annual price declines of about 10 to 20 cents per watt per year on the residential side. The story on the non-residential side, looking at the figure on the bottom, is pretty similar as well. So we are not the only entity out there that publishes data on PV cost and pricing. There are a variety of other benchmarks out there, and folks often want to know how the numbers that we put out compare to some of those other benchmarks. And so we've provided a non-exhaustive comparison on the slide here. And in some cases, the numbers agree. In other cases, they differ. For example, looking at the residential data, the median, national medians from our data set are pretty similar to average installed costs reported by some of the large installers, but tend to be higher than some of the other benchmarks that we show here. And then on the non-residential side, you can see that, for example, the numbers that we show for small and large, for small non-residential systems, agree pretty well with some of the data that Energy Sage is putting out, but are higher than some of the modeled prices, as for example. And these differences, I mean, in the end of the day, they just kind of come down to the fact that, these are sort of apples and oranges. These different benchmarks are based on different data, different methods, and to some extent mean different things. And so it can be hard at times to meaningfully compare them. But, in general terms, they differ from one another for a variety of reasons related to the vintage of the projects, where the projects are installed, whether we're talking about average systems or kind of quote unquote turnkey type systems. So there are a whole variety of different reasons here, but as you can see, the numbers in some cases agree, in some cases they don't agree. We also compare median prices from tracking the sun to international data that the IRENA, the International Renewable Energy Agency, puts out in their annual report. And the data here as well can be a little bit apples to oranges. The numbers for other countries that are embedded in the IRENA report, in some cases, they're based on project level data, sometimes based on survey data. So it can be hard to make really precise comparisons. But I think it's safe to say that, you know, those issues aside, it's clear that installed prices in the US are way higher than what they are in most other countries. And because hardware costs are largely the same, not identical, but pretty similar across countries, it stands to reason that really what's driving most of these differences is soft costs. So, you know, permitting fees, customer acquisition costs, labor costs, all of those sorts of things are ultimately what must be driving some of these differences. Then the last thing I'll note here, just looking at median installed prices, as I mentioned before, you know, we exclude third-party owned systems from our installed price analysis. Just as a little sidebar, we include those systems here and just compare median installed prices between TPO and host-owned systems. And as you can see, they tend to agree. So in the end, the fact that we've chosen to exclude those systems probably didn't have a huge effect on the trends that we've shown, but just for to be safe, we've continued to exclude them. So with that, I'm going to turn to kind of the last main section of the report where we look at variation in installed prices. And this first figure here really, I think, just kind of drives the basic phenomenon home, where we can see the overall distribution in installed prices for systems installed last year. And you can see, you know, really wide pricing variability across all three sectors. That variability isn't even captured in focusing on the 20th and 80th percentiles, as we often do. And that variability, it reflects kind of a whole variety of different factors. Certainly, it reflects characteristics of the projects themselves. It reflects different attributes of the companies that are installing these systems, both their cost structure and their pricing strategies. And it reflects features of the local market where these systems are being installed in terms of the policies and kind of regulatory features of those markets. Throughout the remainder of the report, we look at some of those factors to the extent that we can, both on kind of a descriptive basis, and then we also include at the end kind of a statistical analysis where we can kind of better control for and isolate the impact of individual drivers. There's also a pretty rich literature out there on this topic. Many of those studies we've been involved in or have relied on the Tracking the Sun data, but there's a lot of work that's been done out there to try to understand kind of the drivers behind this quite substantial pricing variability that we see. So the first thing that we look at, and is kind of the most obvious thing, is just differences in system size. And the figures here show that there are pretty clear economies of scale, both within the residential segment and non-residential segment. And so looking, for example, at the residential figure, you know, it's basically $1 per watt difference between systems at the smallest and largest end of the size spectrum. On the non-residential side, the differences are even larger, reflecting the much wider range in system sizes that we're talking about. And as we'll show later when we present the regression analysis, system size is in fact, you know, one of the biggest drivers, at least among those that we can kind of readily identify. Here we show differences in prices across states, and then also overlay on top the median US prices that we showed earlier. And you can see that these, you know, state level prices do vary quite a bit. Importantly, if you look especially at the figure on the left, California, which, as I mentioned, is, you know, represents a large share of the overall data sample, is a relatively expensive state. And so installed prices in California tend to be relatively high, and that in turn pulls that national median up. Most states are at least a little bit lower priced than California, though many are still kind of in that same basic range. And then on the non-residential side, you can see similarly pretty wide variation, and similarly, California tends to be kind of at the more expensive end of the spectrum. Here we show variation in installed prices by installer, focusing just on residential systems and focusing just on the 100 installers with the most systems installed last year. And so the way to read this figure is we've just each dot in the figure corresponds to an individual installer, showing the median price of residential systems for that company last year. And then we also show the percentile range for that company. And we've just rank ordered these installers from lowest to highest price. And you can see that, there is this really tremendous range. Most installers, kind of ignoring the extremes, are somewhere in the $3 to $5 per watt range in terms of their median prices. Half of all installers have median prices above $4 a watt. So there's really a huge level of variability that is kind of associated with the individual installer. Some of that is maybe more directly the result of the markets in which those installers operate, to the extent that they're local firms. But some of it also reflects features of the firms themselves. And so, for example, later within the regression analysis, one of the things that we can specifically look at is the level of experience that each installer has in terms of the cumulative number of systems that they've installed over time. And not surprisingly, we see that does in fact lead to some differences in prices, where installers with more experience tend to have lower prices. You can also see, though, by virtue of the percentile bands, that there's also a lot of variability even among individual installers. And so that, partly, of course, has to do with individual project level features, as well as maybe some level of value-based pricing. Installers, they don't have uniform pricing, and they have some ability to kind of price their systems based on what they think an individual customer might be willing to pay. Here we look at prices based on non-residential customer type. So as I mentioned before, we kind of distinguish between for-profit commercial non-residential customers and tax-exempt non-residential customers, which include schools, government facilities, and nonprofits. And we consistently see that installed prices are higher for systems installed on tax-exempt customer sites. Those differences are especially pronounced in the kind of larger non-residential segment, and in particular looking at systems installed in California. Those differences may arise for a variety of different reasons. Part of it may have to do with the requirements related to, prevailing wage or union labor requirements, which might be a condition for certain government contracts. It might be related to requirements for domestically manufactured components, maybe a greater prevalence of shade or parking structures. And then finally, it could also just have to do with the fact that tax-exempt customers tend to have lower borrowing costs, which might in turn enable higher priced systems to pencil out. Here we look at installed price differences based on module efficiency. Within the residential segment, there's no real clear relationship that we see, at least looking at the data just kind of on a descriptive basis. Within the non-residential segments, though, you can see that install prices do tend to be higher for systems with kind of premium efficiency modules, like greater than 21% efficiency. And that reflects the fact that those modules themselves cost more. The balance of systems costs for high efficiency modules may be a little bit lower, to the extent that you can install these systems on a lower footprint, or alternatively squeeze more kilowatts into a given footprint. But those balance of system cost savings don't seem to be offset, or I would say, seem to be more than offset by the higher cost of those premium efficiency modules. And then finally, here we look at installed price differences based on inverter technology, where we see that consistently installed prices do tend to be a little bit higher for systems with module level power electronics. That's not surprising. Those module level power electronics come with some small price premium. And so we see that reflected in the aggregate installed prices as well. Last, I'm going to turn to the econometric analysis, where we again are kind of focusing on pricing variability, but rather than just looking at it one variable at a time, we bring to bear some more rigorous statistical methods in order to control for correlations that may exist across these different variables and better isolate the impact of individual factors. And so this econometric analysis is really just focused specifically on residential systems installed in 2020, and as with the rest of the installed price analysis, is just looking at host-owned systems. So no third-party owned systems and no systems with battery storage. So here we just provide a little bit more detail on the multivariate regression model. The table here on the right-hand side lists the different variables that we include within this regression model. So some of those near the top relate to characteristics of the system itself. Some of these variables relate to characteristics of the market in which the system was installed. And then lastly, there's at least one variable, installer experience, that relates to characteristics of the installer. The coefficients in the table here show kind of what happens with one unit change of each variable to install prices. So in other words, if you change each variable by one increment, what then in turn happens to installed prices. This next figure here shows those results in maybe a little bit more of an intuitive manner, where we show what happens to installed prices as each of those variables changes either across the kind of percentile band for that variable, or if we switch that variable kind of on or off in the case of the binary variables. So there's a lot of information here. Let me kind of just go through this slowly and see if I can convey some of the key kind of takeaway messages. So looking at the variables in the top of the figure, those are all factors that relate to kind of system level characteristics. The biggest drivers there are system size and ground mounting. So with system size, if you vary between the 20th percentile and 80th percentile of residential system sizes, that in turn leads to about a 38 cent per watt change in installed prices. So that's kind of the effect of the variation, the underlying variation in system sizes. Similarly, ground mounting adds about 40 cents a watt to the installed price of residential PV, though, as we saw earlier, ground mounting is not very common for residential systems. And so looking at the overall variability in residential system prices, ground mounting isn't a huge driver since it's such a small portion of the overall sample. But for those systems that do use ground mounting, that's a big factor in contributing to the higher price of those systems. Some of the other system level variables, so the module efficiency, microinverter, and DC optimizers, you can see that those all tend to also increase system costs or prices, though by smaller amounts. Systems installed in new construction tend to be a little bit less costly. And this, I think, generally makes sense if you think about kind of some of the economies of scope and economies of scale that might exist in, say, large residential, new residential developments where many of the houses may be getting built with solar, and so there may be some economies there that could be leading to lower prices. The kind of middle section of the figure shows what happens to install prices with variation in some of these market level factors. So we look at market size, installer concentration, household density, and median income levels within each zip code. And in general, the variations that we see there are kind of consistent with what we would expect and with some of the prior literature, but generally are relatively small based on the underlying variability in those variables themselves. Similarly, installer level experience, you can see more experienced installers tend to have lower priced systems. But again, that's not a huge driver for the overall pricing variability. The big purple band on the bottom shows the variation in our state fixed effects variable. So those state fixed effects variables basically represent the variation in prices that exist across states above and beyond all of the other factors that we've listed here. So even once we've controlled for those different factors, there still remains a pretty significant residual variability in pricing across states that reflects other kind of unobserved state and local level factors like the cost of living, perhaps retail rates, incentive levels, solar insulation levels, etc. The next slide here shows some of those state level differences more directly and for each individual state. So the dark bars here show those state fixed effects, and those fixed effects are measured relative to California. So basically the dark bars represent the average differences in the average installed price in each state relative to California after controlling for all of the other variables. And we compare those fixed effects to just the differences in kind of straight median prices relative to California, which is what we saw kind of earlier in the descriptive analysis. And in general, we see that the fixed effects do tend to be smaller, which suggests that some of the variability that we saw earlier across states just has to do with kind of some of these other pricing drivers that we've now controlled for. But nevertheless, there does still remain some pretty significant variability. For most states, those fixed effects are kind of within roughly a 30 cent per watt band. So it's not huge, but there are these states at the extremity, New Hampshire, North Carolina, Rhode Island, with much larger fixed effects. And again, some of that, has to do with variables that we haven't really accounted for here. Some of it may just be kind of idiosyncratic features of those markets or of the data themselves. For example, if there's, just a single large installer that dominates a particular market that has very high prices, that may lead to higher average prices in that state that kind of can't really be explained in any kind of fundamental way. So that's it. I've managed to get through 40 slides in just a little over 40 minutes. And so we've got some time left now for Q&A. Before getting to that, though, I did want to just, again, kind of direct all of you to the website at the top here, trackingthesun.lbl.gov. That's where you can find a copy of the report, a copy of all of the other kind of ancillary documents that we published along with the report, including the data set, data visualization, summary briefing, summary tables. All of those things are available there. We'll also be posting a recording of the webinar within the next day or two as well. So with that, I think we've got a few questions, and Naeem has queued them up. So I'm going to hand the mic over to Naeem, who will run through those questions, and some combination of myself, Naeem, and Eric will then try to field those questions.
Great, thanks, Galen. Actually, could you promote me again to host? Unfortunately, I was disconnected, and when reconnecting, I don't see the questions anymore.
Yes, I can do that. I think I may need to. Let's see.
In the meantime, perhaps, Eric, if you could look at some of the questions that are up.
Well, I've got them here too, so I can read them off, Naeem. So first question here, on your coverage, why don't you use behind the meter as the criteria for utility scale? Seems like side of the meter is more important than size. Yeah, I mean, that may be the case, and some of the other kind of market reports out there use kind of behind the meter versus front of the meter as the dividing line. I would say there are kind of two reasons why we do that. One sort of data related and one maybe more practical. The data related reason is that we don't often know whether the system is installed behind the meter or in front of the meter. And so that kind of forces us to use system size as perhaps a proxy. The other reason is that there are and can be relatively small systems that are installed in front of the meter. And our colleagues who publish an annual utility scale solar report, they would rather not have to collect all of the data that they collect for that report, which is much broader in scope than what we've collected here for, all sorts of random small front of the meter systems. And so partly to save them from that headache, we've included them here. But admittedly, it can be a little bit arbitrary and can make for kind of confusing comparisons if you're looking at kind of our sample size relative to some of the other market reports. So hopefully that answers that question. Next question here. When looking through both part 1 and part 2 of the public data set, I couldn't find any Hawaii specific data. How did you pull stats such as the storage attachment rate for Hawaii, for instance? So that is an excellent question and very perceptive. So Hawaii, for all intents and purposes, is not part of our data set. But we do get permitting data from an entity called Ohm Analytics for Hawaii. That data, we haven't sort of ingested it into the overall Tracking the Sun data set, but it does include information on whether or not each system has storage. And so because Hawaii is such a critical state when looking at storage attachment rates, we've kind of opportunistically pulled them into our analysis just for the single purpose of that figure, but not elsewhere. So that's a great question, and this is something that we've thought about in the future, perhaps expanding our Tracking the Sun data to include data from these kind of permitting data sets that are also out there. We have another question from our good friend Chris Marnay asking, is the cost gap between the US and the rest of the world changing over time? And also, was Canada on the chart? So I don't believe Canada was on the chart, but we can go back and check. In terms of whether the cost gap in the rest of the world, whether that's changing over time, we haven't kind of looked at that trend. We have in earlier editions of the report, however, done a similar comparison and have always found a pretty marked difference. And so I don't know whether it's gotten even larger or slightly less large, but there has for many, many years been this persistently large gap between the US and the rest of the world. We have another question asking about system size data, noting that Colorado has the smallest size and higher year-over-year price change, I think, and is the second largest cost state. Any insight on that combination? So that's another perceptive question. So I think the Colorado data for 2020 has some peculiar features to it. There were a large number of systems with very small sizes. And that seemed to be unique to 2020. I'm not sure what is sort of driving that, but that I think is why system sizes in Colorado for 2020 were the smallest among all states, and probably are also why median system prices went up year over year. So that's a great question and a great, just a great notice. Another question, do you have any hypothesis as to what's driving the upward trend in inverter loading ratios? Is it potentially that the market is future-proofing for the system, future-proofing the system for potential hybridization in the future? That could be. I think it also just has to do with the fact that module costs have come down quite a bit over time, and so it's just become more economic to oversize the modules relative to the inverter. That means that you're, potentially clipping a little bit of the peak power production from the modules, but you're operating the inverters at a more efficient load level, and you're getting more power production in those shoulder periods. And so I think part of it is module costs coming down. Part of it, I think, just has to do with also module efficiencies going up, and so because inverters tend to come in kind of fixed sort of increments of system sizes, it may partly just be a function of kind of how module sizes have grown over time, maybe more quickly than inverter sizes have. Question, what are the reasons behind California's high relative system costs? So I think, I mean, there are different reasons, and this is definitely a topic that we've looked at in various ways over time. I think, probably the short answer, which maybe is not all that satisfying, is that system prices, or the cost of living in California is relatively high. And so everything is just more expensive in California, not just PV. But certainly other states also have high cost of living and don't necessarily see such high PV prices. Retail rates are also relatively high in California, and so to some extent, there may be some value-based pricing where systems are priced based on kind of what the market will bear. And we've seen maybe a little bit of evidence for that as well. Naeem and Eric, I want to pause here to see if either of you guys have anything to add on that question as well. If you do, you have to take yourself off mute.
No, not really. I think you covered high labor costs, high cost of living. And then the fact is, within the regression, even controlling for those factors, California has high prices. So, and this is sort of a segue into this next question, which I will take. Someone noted that the regression has a low goodness of fit, meaning the regression does not the variables in the regression do not explain that much of the variation in pricing. And that's absolutely true. We began doing these models 5 or 6 years ago. And back then we had a lot more variables and the goodness of fit was still very low. So if there's one rule in PV pricing, is that it's highly, highly variable. And most of that variation is idiosyncratic. It's for reasons that we don't quite understand. There's been a lot of research on this showing that PV prices are particularly dispersed relative to other products. So it's an astute point. As much as we think we know what's going on, there's some straightforward things like system sizes and economies of scale, but most of the variation in PV pricing we cannot explain.
Yeah, and I mean, some of it certainly has to do with just variables that we aren't able to observe because we just the data don't exist or are too hard to obtain. Things like, for an individual system, did they have to replace the circuit breaker? Did they have to, or the main electrical panel? Did they have to do any re-roofing? There are all sorts of reasons why the cost of a system might be relatively high compared to your bare bones, standard PV system. And a lot of those reasons relate to things that we just don't have great visibility into. So it's unfortunate and something that we're kind of constantly aspiring to get better data on and kind of figure out how we can kind of better account for some of those factors. So I think with that, we have reached the end of the questions. And we've also almost reached the end of the hour as well. So I think unless any other last minute questions arise, I think we will end the webinar a few minutes early. I'd like to just thank all of you for attending. I'd like to thank our sponsors at the U.S. Department of Energy and the Solar Energy Technologies Office for funding this work for many years. We really appreciate it. I also want to thank all of the organizations out there that contribute data to this project. Every January, we send out a big batch of emails to a variety of entities across the country, asking them to send us data. This isn't part of their job, but they do it, and they help us understand the data and work through issues that can come up. So we always like to acknowledge the contributions of all of those entities out there as well. So with that, we will knock things off. And for those that have any questions that might come up in hindsight, please do feel free to email us. I've just listed the email addresses for myself and Naeem here, but we'll certainly share any questions with Eric and Sydney as well, and they'll have the opportunity to weigh in. So thanks again, and we will see you next time. All the best. Bye-bye.